is Arundhathi Krishnan. We'll be speaking on a central limit theorem in the framework of the Thompson group app.
Thanks very much for the invitation to speak here and for organizing the conference. I'll be talking about a central limit theorem in the framework of the Thompson group F. It was Andonika who asked this question about whether it made sense to formulate a central limit theorem in this framework. So thanks to Andu for the nice question and the discussions I had with him. I'll talk briefly first about some algebraic or non-commutative central limit theorems, and then say a little bit about the Thompson group F. Then I'll state and give a sketch of the proof of the central limit theorem in this context. So I'll start with the classical CLT in the context of a classical probability space. So suppose Xn is a sequence of IID, independent and identically distributed random variables. We'll assume for the sake of simplicity that they have mean 0 and variance 1. Then the sequence Sn, which is given by 1 over square root n of the sum of the first n random variables. So this is a rescaled average of the first n random variables. This converges in distribution to x, where x is a random variable with the standard normal distribution with mean 0 and variance 1. So here convergence in distribution, or weak convergence, is equivalent to the convergence of the expectation of f of Sn to the expectation of f of x for every bounded continuous f. So we'll come back to this in an algebraic context, but there's a bad picture of the normal distribution, which is given by its probability density function there. But what we'll do is to restate this in an algebraic context and then talk about other algebraic CLTs. So for this, we'll work in the setting of a non-commutative star probability space. This will be a pair M psi. M is a unital star algebra, and psi will be a unital positive linear functional on M. So we want to think about psi as the expectation functional that we have in classical probability. And the classical setting will fit in here in the following way. Let omega sigma mu be a classical probability space. Omega is a sample space, sigma algebra, and mu a probability measure. Then one way to algebraize this is to take calligraphic L to be the L infinity space. This is a commutative star algebra, and trace mu of f, which is just the integral of f with respect to the probability measure, is a unital positive linear functional on L. So then the pair L trace mu is a star probability space. But often we want to work with the star algebra there, L infinity minus, which is the intersection of all LP spaces. So the intersection of, so the collection of random variables which has finite moments of all orders. So this is to make sure that random variables with the normal distribution actually belong to that star algebra. So sometimes we need to work in that context. And in this non-commutative probability space, what is a random variable? We want to talk about random variables and what convergence means in this context. So in a star probability space M psi, a random variable is just an element x of the star algebra M. And we'll only work with self-adjoint random variables, so x equal to x star in M. And we'll now say what convergence in distribution means in this algebraic setting. So let an phi n be a sequence of star probability spaces. A phi is a star probability space. And we have this sequence an of self-adjoint elements of an. X belongs to the star algebra A, so these are random variables. So we'll say that the sequence an converges in distribution in this algebraic setting to x, and denote it that way if we have the following. So the limit as n goes to infinity of phi n of an to the d is equal to phi of xd. So we're saying that the expectation of the dth powers of an, this limit, the limit of this sequence is the dth, the expectation of the dth power of x. So we're really looking at convergence in terms of moments, because that's what makes sense in this algebraic context. So that's convergence in distribution for a star probability space. And now we'll go back to our classical central limit theorem, but stated in this context. So an algebraized classical CLT. let A phi be a star probability space where A is commutative. And suppose AN is a sequence of independent, that's sometimes known as tensor independent, and identically distributed random variables. So both these properties are defined in terms of the expectation functional phi. And we'll assume again, for the sake of simplicity, that each of the random variables has mean 0 and variance 1. So phi of an squared is 1 and phi of an is 0. So then 1 over square root n of the sum of the first n random variables. The sequence converges in distribution to x, in distribution in the sense that we just saw, which means that the limit of the dth moment of the sequence is equal to the dth moment of x. And x here will be a normally distributed random variable of mean 0 and variance 1. So we just restated the classical CLT, but in this context. And it perhaps seems like it's a weaker formulation because we're only talking about the convergence of moments, but the normal distribution is uniquely determined by its moment. So it really is an equivalent formulation. So, well, the advantage of stating the central limit theorem in the algebraic context is that we can now talk about other algebraic CLTs, where the sequence AN may not be tensor independent anymore, but satisfy some other property. And this is what we'll do. The most well-known of these, of course, is the notion of free independence. And I'll just go over the definition here. We did hear about it a couple of days ago. So a sequence of random variables, AN, in a star algebra A is freely independent if, when you have that calligraphic AI is the unital star algebra generated by little ai, we have phi of products of this form is 0 for all k and n when these conditions are satisfied. So phi of each xj is 0. Each xj comes from the unital star algebra aij, and neighboring indices are not equal to each other. So I1 is not equal to I2, I2 not equal to I3, and so on, up to ik minus 1 not being equal to ik. So each of these xi's, neighboring xi's come from different star algebras AIs. So in this case, if we have that whenever phi of xj is 0, then phi of this product is 0, then the sequence AI is freely independent. And then we have the well-known free CLT of Voiculescu from 85, which states that if A phi is a star probability space and AN is a sequence of self-adjoint again and freely independent rather than tensor independent and identically distributed random variables, we'll assume again that phi of AN is 0 and phi of AN squared is 1. Then the sequence 1 over square root n multiplied by the sum of the first n random variables, this converges in distribution in the algebraic sense to S. And S here will be an element with Wigner's semicircular distribution of mean 0 and variance 1. Not a bad picture, but it really is a semi-ellipse rather than a semicircle. And that's the density function there. So Voiculescu proved this using analysis, really, and the notion of R transforms. But then in 1990, Spiker gave a proof using the combinatorics of pair partitions. And well, both this free CLT and the algebraic classical CLT we looked at, there's a very nice exposition of them in the textbook of Nika and Speicher, which really talks about how they're connected to pair partitions. So I will say something briefly about pair partitions because they'll come up again when we're looking at a CLT in the context of the Thompson group. So pair partition is exactly what it sounds like. It's a partition of a set into pairs, into a disjoint collection of pairs. So we typically have a pair partition pi. We want to be d over 2. This is a partition of the set D, which is the set from 1 to D. So each VI is a subset of D. I not equal to j means this intersection is empty, and the cardinality of each VI is 2. And we'll denote the set of pair partitions by P2 of D. And once you have pair partitions, you can talk about crossing and non-crossing pair partitions. So I just have examples here. We'll look at D equal to 6, and we have an example here for crossing pair partition. So we can write the pair partition as 1, 3, 2, 4, 5, 6, but really it's the picture that shows you why it is a crossing pair partition. The pair 1, 3 and 2, 4 will cross each other. And here's an example of a non-crossing pair partition of 6, 1, 6, 2, 3, 4, 5, and you can see there are no crossings here. So well, what does this have to do with the central limit theorem is the following. So let's look at the number of pair partitions, all pair partitions, and the number of non-crossing pair partitions. So the number of all pair partitions of D, this is very easy to see. It's just the number D minus 1 double factorial, which is D minus 1 multiplied by D minus 3 and so on up to 1. And the number of non-crossing pair partitions, the set T, is given by the D over 2 Catalan number, which is given here by this formula. And these numbers correspond precisely to the dth moment of the two distributions that we've seen so far, the Gaussian or the normal distribution and the semicircular distribution. So D minus 1 double factorial is the dth moment of the normal distribution, which is what popped up in the classical CLT as the limiting law. And the Catalan numbers are the dth moments of the semicircular distribution, which is the limit law in the free CLT, in the case of the free CLT. Of course, in both cases, this is for D even, and in both cases, the odd moments are all 0. So really, we have this question about limiting laws, and convergence in distribution, but they connect to the combinatorics of pair partitions. And then, so this was in the case that we first had the case that the sequence AN was tensor independent, and then that it was freely independent. So you can look at what else you can do with that sequence AN. What property can you generalize to? So there's this generalized CLT, which was proven apart by, well, I think both these papers, Speicher and von Waldenfels, and also Božejko and Speicher, both in '94. The theorem, this generalized CLT says that if you have a star probability space A phi, and you have a sequence of self-adjoint elements AN, which satisfy two properties. The first is an invariance principle known as exchangeability. So Klaus talked about this in his talk, but this says that the joint distributions remain the same when you permute the indices under the action of the infinite symmetric group. And the singleton vanishing property. So that means that products of the form where, let's say, A1, A2, A3, okay. So something like this would be 0 because A1 appears as a singleton. So that's the singleton vanishing property. And in this case, we take Sn again to be the same sequence, 1 over square root n of the sum of these first n random variables. Then the limit of the dth moment of Sn is given by this right-hand side. So we're summing over all pair partitions pi of D, and we have a number here phi pi, which depends on the pair partition, and it's given here as being phi of a product of this form, where pi is the kernel of L. So here by the kernel of L, we mean the partition of D into the level set of the tuple L. So here's a little example. We have phi of a product in this form. This gives the pair partition pi given by the level sets of L. So we see that A3 and A3 appear there. So we have the pair 1, 3. And then A1 appears in the second position and in the seventh. So we have the pair 2, 7, and so on. So you can write down the level set, and that'll give you a pair partition. So this is an even more general setting where we're not assuming independence, but assuming exchangeability and this property of known as singleton vanishing property. Okay, so what we'll do is to look briefly at the context of central limit theorems in the context of group algebras, and then come to the Thompson group F. So often you might look at the limit distribution of a sequence that comes from a group algebra of a group that you're interested in. And Philip Bian in '95 worked in the context of the infinite symmetric group, S infinity, the group of all finite permutations. And the sequence that he worked with came from the sequence of star generators of S infinity. And he worked, the expectation functional there came from, was a canonical trace from the left regular representation. And the CLT in that context gave the limiting law was the semicircular distribution. And then more recently, first Kursler and Nika, and then Campbell, Kursler, and Nika, worked again in the same context of S infinity, but with a different expectation functional, and had central limit theorems in that context. Gero Fendler in 2003, I do not know how to use this, worked in the context of Coxeter and Artin systems of large and extra large types, and showed CLTs in this context as well. And so because we had been looking at the Thompson group F in a different context with respect to just connections with non-commutative probability, we Andu said, let's look at this question. So Thompson's group F is one of the three groups that Thompson introduced in 1965, and it was introduced as a subgroup, a certain subgroup of piecewise linear homeomorphisms on the interval 0, 1. But really, for the purpose of this talk, we're only going to work with its infinite presentation. So F is given by generators G0, G1, and so on, and these relations here. Gn, Gk is Gk, Gn plus 1, whenever k is less than n. So we really will work with these relations and what happens there when we do a rewriting given by these relations. So what happens is that the generator of the smaller index, Gk, just goes over to the other side and it remains the same. But the generator of the larger index, when it goes over to the other side, it has its index go up by 1. Just an example, G7, G3 is G3, G8. You can also represent F, for example, using rooted ordered binary trees. And there's a lot about this in the PhD thesis of James Belk. Okay, so we're going to work in the context of the group algebra of F. So CF and phi is our star probability space. CF is the group algebra, and phi is the canonical trace, which is defined on elements of F by phi of x equal to 1 if x is the identity and 0 otherwise. And it turns out that in this star probability space, if we look at a sequence of elements that come from the generators of F, we do in fact have a central limit theorem. So we take An to be the sequence of self-adjoint random variables in this star probability space, which is given here. So we look at the generators of F, take Gn plus Gn star. We represent the elements of F in the group algebra using the same notation. So Gn plus Gn star, or Gn inverse, divided by the square root of 2. The dividing by the square root of 2 is just to ensure that they have variance equal to 1. And then we take Sn to be the sequence given by 1 over square root n, sum of the first n random variables, but the indices start from 0 rather than 1. And in this case, we do have limiting moments. Turns out that the limit as n goes to infinity of phi of Sn to the d is 0 when d is odd, and d minus 1 double factorial when d is even, which are just the moments of the normal distribution, which we saw a little while ago. So that's theorem. The rest of the talk, I'll sort of give an idea of the proof. I'm not going to be very rigorous about anything, but I'll use an example to illustrate most of what we want to see. So we just start by writing what the dth moment of Sn looks like. The phi of Sn to the d, I'll just go back briefly to the previous slide. Sn was given in terms of the ans, and the ans in turn are given in terms of the gns. So if you expand Sn to the power d, you end up with this thing on the right-hand side. So you have 1 over 2n to the d over 2. And then this summation of phi of products like this. So I'm just going to write that down here because I'll come back to it. I'm going to say that we have phi of Sn to the d is 1 over 2n to the d over 2. Then I'm just going to write down it's a cardinality of a particular set. So because phi is just the canonical trace coming from the regular representation, it's either 0 or 1, and we only have to count how many times it's equal to 1. So we're really counting the cardinality of this set, which we write as W0 dn. So that's the set here. So we have pairs of tuples I and epsilon. And from here on, I'm going to think about these pairs of tuples as words, which are composed of elements coming from F, either generators or their inverses. And these words are of length d. So the tuple I goes from d to 0 and minus 1. Epsilon goes from d to minus 1, 1. Epsilon just says whether the letter you're considering is a generator or its inverse. And I can take values from 0 to n minus 1. So we're drawing from the pool of the first n generators and their inverses of the Thompson group. And of course, we want this product to be the identity. So we think of this product as the evaluation of the word that we're considering. So we want words that evaluate to the identity of length d, and which are composed of the first n generators and their inverses of f. So it's really just it's just a question of counting these or approximating how many of these there are, because we're going to be concerned with the limit as n goes to infinity. So here's a sketch of the proof. I'll just go over the steps that we consider in the proof. Step 0 is just a couple of observations. The relations in f are length preserving. So this means that only words of even length d can evaluate to the identity. So you get right away that all the odd moments are 0, which is what we wanted. And the next observation is that any word that evaluates to the identity must have an equal number of generators and inverses. I will say, however, that we spoke about the generalized CLT. So this doesn't fit into that framework because the sequence AN here is not exchangeable. And it also doesn't satisfy the singleton vanishing property. So it doesn't fit into the framework in the context of that theorem. Okay. So our first step will be to take each word, which we write as this pair of tuples, and reduce it to a normal form. And we're going to show that this normal form is actually unique. So the normal form has a very specific form. What we're doing is to move over all the generators to one side and the inverses to the other side. And then we're going to order the generators in a particular order. The technical condition is given here, but essentially the indices are, for the most part, decreasing. And once in a while, they might remain the same or go up by 1. It's just a technical condition, but we'll see an example of it on the next slide. But the advantage of bringing a word to its normal form is that you can see very clearly why it evaluates to the identity, whereas in its original form, it may not be evident. So it's just a way to make it clear that this word is actually going to evaluate to the identity. I should say that you can bring any word to a normal form, not just those which evaluate to the identity, but these are the ones we want to count. So just an example. We started with the word given here. So just by looking at it, it's not clear that it should evaluate to the identity. You'd have to work out the relations. But by working out those relations, you can bring it to this normal form. And then it's really clear that the G0 cancels out the G0 inverse, G3 with G3 inverse, and so on. So this is actually going to be the identity. Now, one might think that the normal form of the identity should just be the empty word. But here we really want to bring it to a form where we're preserving the length so we can count how many of them there are. And we'll show that this normal form is actually unique. There are probably many ways to show it, but I stumbled upon abstract reduction systems, and it just gave a very neat way of showing that you can arrive at a normal form. So I'm just going to say something briefly about these. So in general, an abstract reduction system is a pair A and arrow. So A is a set, and this arrow just denotes a relation on A. So it's a subset of ordered pairs of A. But we use the arrow, or they use the arrow in this context, because it really signifies that you're rewriting a word or reducing a word. So it really shows you that transformation. So we'll take A to be the set of words in F, and we'll define a reduction given by arrow. And the reduction just comes from the relations satisfied by the generators of F. So we'll actually work with 2 reduction rules, but I've just got one example here. So if you have a word which has a subword where there's an inverse to the left of a generator, you want to make sure the generators are to the left. So you can define what the rewriting should be depending on the indices K and L. So you can write that down. And so you're going to see the reduction is given by performing this rule on all subwords where something like this occurs. And then you can do the same thing to order the indices in a particular order. You can do that in another step, or you can combine them. It comes out to the same thing. And then you have to show 2 things. One is that this reduction is terminating, so it's going to end at some point. You won't have to keep doing it forever. And also that satisfies something known as local confluence or just confluence, which roughly means that if you can do two rewritings in different parts of the word, it doesn't matter what order you do them in because you can still converge back to a common point. So that's confluence or local confluence. And so using that, and there's a, I think, very well-known lemma in the field known as Newman's diamond lemma, that will give you that each word has a unique normal form under this rewriting. And so we can do that for our words which we want evaluating to the identity and bring them to a normal form which we also now know to be unique. So the next step will be to use that unique normal form and assign a pair partition to each word that evaluates the identity. So we're going back to counting in terms of pair partitions. And I've just got an example here. So this word here is in its normal form. And there's a very clear way to pair generators with their inverses. They just, they'll form this rainbow pair partition as it's known because of how it looks. And then what we'll do is to trace back to the original word which arrived here as its normal form and pair the generators with the inverse with which they'll eventually cancel out in this normal form. And they may not be equal to each other. So for example, we have G18 inverse here, it's paired with G16. So the indices there are not equal, but they will be equal when they arrive at the normal form. So we can go back and assign this pair partition, which is 18253647, to this word which evaluates to the identity. So you can, this is an example, but you can sort of rigorously show this for any word that evaluates to the identity can be assigned a pair partition. And then the question becomes, well, how many words go to each pair partition? Because that's what we need to count in order to get this limiting distribution that we were looking for. So that's step 3. We'll say that ND and pi, so it depends on the length of the word D, the number of generators we can draw from N, and pi is the pair partition. So how many words I epsilon are assigned to the pair partition pi? And we're not going to find the precise number, but we'll find bounds in it, which will allow us to calculate our limit. So that was the last thing I wanted to write down. So we can now rewrite this dth moment as the summation over all pair partitions of D, and then that number ND n pi, which we won't find exactly, but we'll find bounds on. So this is a sort of just a verbose way of saying what we can prove, write down more rigorously. But so a key observation is that suppose we're given a word that's assigned to some pair partition, and we know we want it to evaluate to the identity. And suppose we know all the generators, but not the inverse generators. And suppose those generators satisfy the condition that their indices are sufficiently spread out. You can quantify that more precisely. Then you can fill in the inverse generators in a unique way to give you a word that will evaluate to the identity. So here's an example again. We know that we have G0, G75, 2550, so they're all 25 apart from each other. But we don't know what these inverses are yet. But there really is only one way to fill them in so that these will be the pairs that get formed in your pair partition. So I fill that in here, but I'll just say sort of briefly how this happens. So what we do is we start by looking at the generator of the smallest index. We know that nowhere in the relations is that index going to change. So this one's an easy one, G0 just gets paired with G0 inverse. We had G25 here, which is paired with something, and all the other indices that we knew, 50 and 75, are much larger than 25. So we can be sure that this is going to be 25 inverse. So you can sort of fill in the missing inverse generators in a unique way. And yeah, the key observation is that you have relations of this form, right? G0 remains the same. It's only the generator with the larger index that changes. And then precisely how much an index will change is given by the number of crossings in the pairs, in the pair partition that you want to get, that you're given rather. And so the upshot here really is that you only have the freedom to choose half of the word, roughly speaking. So d over 2 of the indices from this pool 0 to n minus 1 for a word to be the identity. And the point is we're going to look at the limit as n goes to infinity, so this pool is getting larger and larger. So we can really assume that the generators are very spaced out. because n is going to get larger. So we can then get these bounds on nd and pi. It doesn't matter too much what they precisely are, but roughly this factor here on both sides looks like n choose d over 2. We can really kind of ignore everything else because we're going to normalize by 2n to the d over 2. So roughly both of these n's are approximated by this number here, where you're going to have a lot of cancellations. And going back here, I think I missed something out. I should have had 1 over 2n to the d over 2 here. So we're going to divide by that in order to get the dth moment. So we'll divide these inequalities by 2n to the d over 2, and then sum over all pair partitions, which is what we wrote here. And then we're going to look at the limit as n goes to infinity. So you'll essentially end up with the limit of the dth moments of Sn bounded on both sides by the summation over all pair partitions of just 1, because a lot of cancellations are going to take place, and these numbers are just the number of pair partitions, which is d minus 1 double factorial. So you end up with that on both sides, and that tells you that the dth moment of Sn in the limit is just d minus 1 double factorial, and we already saw that the odd moments are all 0. So I'm just going to recap in the next slide. So we started by f generated by GNs, which satisfy these relations. That's our Thompson's group F. I should have said earlier, but of course the generators don't commute with each other. But we still end up getting in the limit distribution, the normal distribution, but of course they don't commute with each other. What we did was to take an to be a self-adjoint sequence coming from the generators, which we've normalized so that it will have mean 0 and variance 1. And then these rescaled averages Sn, 1 over square root n, of the sum of the first n random variables an. These will converge in distribution to x, where x is a normally distributed random variable of mean 0 and variance 1. And like I said, when we talked about the classical CLT, the normal distribution is uniquely determined by its moments. So we can really talk about weak convergence of the probability measures that come from Sn to the probability measure of the normal distribution, because the normal distribution is uniquely determined by its So some sort of big questions, which I really haven't started working on yet. But the first is, well, what is so special about the relations satisfied by F? What is it there that lets you make this association with pair partitions? Clearly, it's because you can pair a generator with a certain inverse, even though the indices are not the same. As I said earlier, even though we're making the association with pair partitions, the sequence is not exchangeable and doesn't satisfy the singleton vanishing property. So you can have products of this form not being equal to 0 in the case of the sequence an here. And sort of a partial answer, it's a very broad question, but recently Aiello extended this central limit theorem to Brown-Thompson groups, where the relations are slightly different or more general. So Gn, Gk is Gk, Gn plus P minus 1. So rather than just Gn plus 1, you have this P minus 1. So P is equal to 2, it's this Thompson group. But otherwise, you can talk about more general Brown-Thompson groups. And well, all of these arguments just work in this case as well. And then the question would be, as in the CLTs, in the case of the infinite symmetric group and so on, it's possible there to ask about a multidimensional version. So if you were looking at mixed moments and the joint distributions there, can we sort of frame that appropriately here and hope to get the multivariate normal distribution is the question, but it's not something I've looked at all. A few minutes left, but it's the last talk before lunch, before the free afternoon, so I'm going to stop here.
Questions for Arundhathi?
So if you take the sum of the first n and then the sum of n plus 1 to 2n, you get two Gaussians. Are they independent, or what's the relation? Is that what you mean by the multivariate or something else?
Yeah, you sort of have to choose which of the, you can basically look at some kind of injective function which goes from 1 to n to the set of generators, and it's sort of, which injective function should you choose, and for which can you say something meaningful. I haven't, maybe you only picked the odd ones and the even ones, or what you described, but it's not something I've looked at all yet. But again, you'd be working with the relations and how, how things can cancel out.
Other questions?
Is there a way to realize the Thompson group into some more select formula setting, like a matrix group?
Not that I'm aware of. I know you can.
And realization.
Yeah, so one way is to look at these homeomorphisms in 0, 1, which are piecewise linear, and so you can work with that set of functions. Or people work with binary trees. You can describe all of the generators in that setting, in that concrete setting. I'm not aware of the context in the matrix group, though.
So here you work all the time, these examples you wrote, you work with canonical trace.
Yes.
So do we know for the Thompson group, essentially,
Are there
what other traces? I mean, what should we expect?
So I think Gauss and Rothko showed that with traces, they've sort of characterized the extremal characters of F, I think. So there is really no other trace, but perhaps there's a state which is not tracial that you can. We talked about this briefly.
This one can characterize all extremal characters on the Thompson group.
Okay.
And they are either coming from the left regular representation or from the degenerate one-dimensional representation, which are parametrized by the unit circle.
Okay.
This means if one would have a continuous extension of that would solve the unit problem.
But maybe one can have a state which is not tracial,
Sure.
related to the length of a word or something like that.